funders with the Laidlaw Foundation for this. Disclose any vested interests. I'm not being funded by Google, don't worry. So what is AI? First thing you think might be this, right? The kind of Terminator thing, but that's not what I'm talking about here, weirdly enough. That'd probably be a very much more interesting talk, but never mind. What I'm talking about is kind of computer-controlled equipment, to use Osborne and Frey's term. I'll talk about them in a minute, which is used to automate the 18 different types of capability listed on the side here, as classified by McKinsey. So these are the things which make up human tasks, how humans act, how humans behave, for them. So stuff from information retrieval all the way to motor skills and back. I should note here that I don't exactly follow McKinsey's classifications. We break the top category into two. So we thought bundling sensory perception that is visual and non-visual together is kind of a bit of a false classification. There's a lot of diversity in the field of automating sensory perception. So we break that down into visual and non-visual perception. But yeah, so when you think AI, in this talk when I refer to AI, it's computer-controlled things which are trying to automate any of those things, basically. So yeah, you might have heard of a few kind of current approaches to this. This one specifically made a lot of news when it first came out because it was the first forecasting attempt. And these are the two kind of main ones. It's a report by the McKinsey Global Institute in 2017, and then a report by a couple of professors at Oxford at the Martin School in 2013 that was republished in 2017. Now there are others, but these are the two main attempts to forecast the development of kind of artificial intelligence over time, both where the technology will go, which is what I'm talking about, and the implications of that on the labour market, which I won't for today be talking about. Now, they both follow kind of a broadly similar methodology. I am kind of abstracting a bit away and simplifying it a bit here, but I think this does it justice. Basically, what they do is they get a set of experts, sit them down in the room, give them some things to label, potential jobs, and label them in a binary way, so say whether they're automatable or not automatable by 2050, which is the kind of the standard time horizon for this. They then take a machine learning algorithm, in the case of Osborne and Frey, Gaussian classifier, for example, and they get some poor research assistant, I assume, to classify each one of those jobs by kind of the subtasks that make it up. So say it was giving this presentation, it would be potentially stuff like language generation, audience engagement, hopefully, or things like that. And then what they do is they then train the algorithm on the set of jobs that they've got labelled, label all the jobs in a general purpose database, typically the ONET database compiled by the Department of Labour here in the US, and apply it, and then use that as the basis of their forecasts. So use that to say which jobs will be automated in 2050, where the technology will be, and so on. There is a kind of a problem with this methodology, though, because the use of this kind of algorithm means that the outputs are only as kind of good as the inputs. Their results are only as good as the predictions of the experts that they get to label the first set of jobs. Because I mean, I guess it doesn't matter how good your algorithm is and stuff like that. If it's fed labeling data that's incorrect, it's not going to produce correct outputs. Or if it's fed labeling data that's unreliable, it's not going to produce reliable outputs. And this is where the problem comes, because we don't have much reason to assume these kind of predictions about what will be automated by 2050 and so on are reliable. Expert prediction is notoriously unreliable in areas. So I'm using an example from Armstrong et al.'s paper in 2014 of a Boeing engineer. That was their prediction for the biggest plane, 10. As a few of us have come here on planes bigger than 10, which can hold more than 10 people, I think that one's probably false. That's true as well, yeah. But I don't know about the engineering challenges of building a car versus a plane. I assume it's harder to build a plane, but not my area of expertise. And yeah, so this is a prediction from the late 1950s about AI specifically. And again, if artificial brains are around by now, I haven't noticed them. I don't know whether anyone else has here. Yeah, basically there's the kind of common aphorism that AI is always 10 years away, right, in terms of predictions. And this is a big problem for these kind of approaches, because I mean their entire approach relies upon these predictions being reliable. If the predictions are not, then their training data is not reliable, so the kind of mappings that they use the algorithm to create are themselves not reliable either. And this has been pointed out a couple of times already in the literature. An example given is that in the 1960s, 1970s, it was thought that CEOs would be automated within 10 years, for example. That, again, obviously hasn't happened. Now, one argument that it doesn't require this kind of reliability might be a kind of a wisdom of crowds argument. So if you could use kind of a central limit theorem, law of large numbers type approach over the predictions, you could say it doesn't necessarily matter that each individual one's not that reliable, but all put together, the average will be reliable. But there's no reason to assume the mean estimate of these predictions are a good approximation of reality either. You might have some futurists going out and saying everything will be automated within 30 seconds or whatever. There's not necessarily a finite variance in predictions, and if so, kind of it needs to be stated in the literature again. So, yeah, it looks like we don't have a very good reason to believe the approaches that have been pursued already, or believe their outputs. And this is where agent-based modeling can step in, I think. So instead of getting experts getting to make predictions and basing your kind of forecasts upon that, what you can do instead is you can just simulate the firms. Kind of use object-oriented computing to simulate the firms doing the innovations themselves. And in theory, it should also be able to, I think, be able to get around the issues of trend breaks in the data, purely because if enough of the predictive power is endogenized, so if the agents are simulated to a very, very accurate degree, they should change their behavior in response to stimuli in the kind of way which the trend where the trend would change. Yeah, I'm not sure whether that assumption applies to what I'm going to present in a minute. I don't think our model is fine-grained enough to do that, but you can. The assumption, well, what I was saying is that in theory, if you endogenize enough stuff and you have as accurate enough a prediction, accurate enough a model of all the firms in your ecosystem, you shouldn't fall victim to trend breaks that can kind of standard time series forecasting models. But again, that's more of a speculative approach. That hasn't been the focus of this project at all. Claiming this project could do. This is just kind of a speculative bit. Yeah, but even regardless of that, you've got an advantage in doing it this way, which is empirical realism. You don't need this expert speculation. Even if you're not modeling the firms in a massively fine-grained way, you can still model them empirically instead of using future forecasts, future guesses, which gives you more of a reason, I think, to believe the outputs of these models than you would have to believe models based upon these kind of expert guesses. So with that in mind, should talk about the model that I built, right, or we built. Yeah, so this is the model we built. We attempted to do this. It's called FORTEC. What you see here is just a network diagram of the collaboration between the different task areas. So as you can see, different kinds of task areas seem to interact with each other a lot more. Specifically, a lot seem to interact with supervised learning and unsupervised learning. But yeah, so what this model is it's kind of aimed to be a large kind of empirically based agent-based model, as opposed to, say, a toy model. And it aims to kind of cover the labs and the firms, to model them, the ones that are doing research in some kind of technological field. And hopefully, it should accurately simulate the behavior of firms up to a certain time period. And it's a forecasting model. So I should add a note of caution. towards this. Famous quote there by George Box. But kind of what I'm going to use it to say is that we're not attempting to simulate every single behavior that could be carried out by the firm. We're not attempting to simulate what someone in HR has for lunch, for example. Like, what we're just trying to do is simulate the behaviors that are useful and that are relevant for this kind of area of prediction. And I will go into kind of how we've done that in a second. And also, the intention of the model is not as kind of the last word in prediction. It's not as the best possible agent-based predicting model you can do for AI or for any high technology domain. The idea is to create a foundation for other researchers to build upon, because there don't seem to be any kind of empirical prediction models, predictive agent-based models out there yet for high technology industries. There's toy models, but we wanted to kind of do better than that, to draw directly from empirical data. So when I lay out the model, I'm just going to say and do it as follows. So going to go for how kind of basis of the model to start with, and then what we're simulating, what we're trying to forecast specifically, what the agents are doing, and kind of their network setup. The final part. So, firstly, what?
It looks to me like you're heading towards a single point forecast, rather than, say, subset sensitivity.
I mean, I don't want to spoil this. I'll go into that later.
Okay.
Yeah, so what we're simulating is we are simulating research labs, firms, and startups in the US, to start with, working on AI, as defined earlier. And when I mean research labs, I mean both university labs and private labs, such as, Google's labs, for example. And the way we approached this was by building from the empirical data upwards. So we compiled quite a few large data sets. So we found a AI startup data set by the venture capital analysis firm, Venture Scanner. We found a robotics startup data set from a trade magazine called Robot Report. We went through the stock market listings that NASDAQ do of all the major stock markets in the US. And we went through the QI Universities rankings. And from that, we attempted to extract every single AI startup, AI research lab, and firm working on AI in the US at the minute. By in the US, I mean based in the US. And these are the figures that we got for that. I should note with how we classify them as well. If a firm does multiple of these kind of task types, is trying to automate them, we treated those parts of the firm as separate firms for the purposes of this model. It makes the next parts of it a lot easier to do computationally. That could be something for further research to work out a way of kind of mashing them together into a more accurate firm-based structure. Yeah, so in terms of what we were trying to forecast would be the level of automation for each of these tasks in 2050. And what I mean by this is relative to human ability, how much can be done by computer-controlled equipment. So say if it was 0.5, for example, that a level of automation of 0.5 would designate that the machine was able to perform half of the kind of possible tasks that humans could perform. And that'd be 10 times the level, so they could perform the easiest half of the tasks that people could do. It was done this way because it meshed quite nicely with ONETs, an ONET classification that I will talk about later. So now you're probably wondering, what do the agents do in this model? So we've got these agents, what do they do? In this order, they kind of receive funding from venture capital firms and such like. They collaborate with each other, they try to launch joint ventures or look at each other's research papers, steal trade secrets, whatever you want. They then spend the money on research projects. Information then diffuses throughout the system, and firms might enter or exit the market just after this point. And then the whole thing repeats itself for each time step. And sorry, the table was meant to go where table 1 was. I knew I'd missed a label somewhere. But yeah, okay, so what that was meant to be was the table I showed you earlier, automation potentials at the minute. And how we got that was we took the McKinsey task types, we matched them up to the ONET abilities characteristics. So ONET gives for each job a set of the abilities that it requires to do the job. We matched those two up, took aspects of jobs, or in some cases full jobs, that have been automated by now, by the end of 2017, which is when we start the model. And from that inferred that the level of automation for that type of task must be at least there. So it must be at least at the point at which we can automate the jobs that we see are automated now, or the aspects of jobs that we see are automated now. So once we've got those initial conditions, we then use the data set to try and derive relationships for firm funding. And this, what I show you here, is the distribution of funding, by which I mean stuff like research grants, venture capital grants, wealthy investors, Amazon buying you, those kind of things, over the entire data set. And as you can see, it is kind of very, very clustered around kind of a small level value, but you still get some very large values as well. It in fact follows a inverse Gaussian distribution, or at least in the data set followed an inverse Gaussian distribution. And then we used that as well as relationships in the data set. We compiled the number of successful research projects which firm carried out. We took a panel of data for firms, and then compiled the number of successful research projects they carried out over a year's time period, and then looked at their funding for the previous year, as well as, the other way around. We looked at what they did the year before and the funding the year after. And obviously ran loads of controls as well. But this is the most important result, and when we use in the model, we find a statistically significant relationship between the number of successful innovations in a previous time period and the funding that the firm receives in the next time period. A time period is defined as years, in this case. Now, in terms of their research, agents can pursue two strategies. They can pursue radical research, the kind of trying to shift the paradigm, trying to develop a new technology, an entirely new technology or way of doing things, or they can pursue incremental research, which is where they kind of build upon other people's work, recombine pieces of work, and so on. And the probabilities that they'll do this, we found, were 25% for radical innovation, 75% for incremental innovation. This was compiled both from an MIT Sloan review study in 2016, which is the one referenced, of all firms generally, and also a 1995 MIT Sloan review study of specifically high technology firms. Because the two of these matched each other so well, we thought that it would be admissible to use this. And the strategies have different chances of success and give different payoffs. So the payoff for an incremental innovation was defined over a uniform distribution over a kind of a small space. So it's 0 to 0.0001 of the total human level at a task. And then radical research was defined over a log normal distribution, the payoffs. The kind of intuition for this was, while most of the kind of radical projects we saw in the literature were still quite small in terms of their impact, there are some which are very, very large. For example, the first people to use Twitter's Firehose API to try and develop algorithms for understanding natural language, for example, that had a massive payoff for the field and changed the paradigm in the field. So hence we defined it as a fat-tailed distribution to capture that. And yeah, we have networks. A network which is formed between the labs which collaborate now. Sorry, this isn't a particularly easy to see picture, but this is this was the network with a Kawai force algorithm spacing. So as you can kind of see from that, there are some firms which emerge as ones with lots and lots of collaborations, those in the center, and some firms which don't have very many people they're collaborating with. Obviously, where collaboration, sorry, I should have said, is denoted by an edge between the two nodes in the network. And those would be the kind of firms out here. And now, yeah, so the graph model was a random dynamic graph that they were situated on. And at each time step, the firm tries to collaborate. Firm or lab, sorry, tries to collaborate. And the probability they will kind of form a link with another lab in a time period was calculated as 0.718. So for all the network data, the way we went about getting it was, instead of directly empirically observing it, because there didn't appear to be a good enough data set on that, we took a data set compiled by Mark Newman at Santa Fe Institute of the network characteristics for these kind of networks and worked backwards using the behavior search genetic algorithm.
So, probability, what's D?
Sorry, there's meant to be degree. So the probability it's meant to be probability they will form a link, form an edge with another node, given that they make an attempt to do it.
So it's not what the words say. The words say the probability that they try to collaborate. This is given that they try to collaborate, the probability that they succeed. Is that correct?
Yeah, sorry. Yeah, that term's probably ambiguous. I apologize. Yeah, this is the probability that given that they try to collaborate, they succeed. And so this probability was derived, yeah, from overall network characteristics that we were able to find.
So does it require both nodes to attempt to collaborate with each other?
No, as this is a single node trying to form a link with its peer.
So this is the probability of any two nodes. So
Yeah.
each lab only attempts to collaborate with one other node.
Yes. Oh, well, in a time frame, this is repeated 4 times, I was about to say. But for each time they attempt it, for each time they try to collaborate with someone, this is the probability that it will be a success, that an edge will be formed between the 2 nodes.
So every time step, a node attempts to connect to 4 other nodes with some level of probability of
Yes.
success. And are those connections persistent over time steps?
I think I'll come to that in a minute, if that's all right. If not, because there's a couple more slides on the network stuff. But yeah, so they have a preference over who they collaborate with as well. So when they're trying to pick who they collaborate with, so they collaborate with someone with that probability, 0.718, and then they've got to decide who they're going to collaborate with. So they pick a lab of the same task type, where the task types again are the ones defined by McKinsey plus the extra one because we split sensory perception up with that probability there. And obviously the partner they pick is not that with 1 minus that probability. And they also have kind of a preference over the expertise of their collaborators. So they generally try to pick someone of very, very similar expertise to themselves, which is something qualitatively seen in the literature, but we were able to draw it out here with quantitative analysis, the probabilities. And specifically, they pick, if they want to collaborate with someone of similar expertise, they do so over quite a tight space of kind of expertise. Sorry, by expertise I mean the research level the other lab has, like the amount of research it's done. And the actual figure for that is 0.001, if I remember rightly. So these firms are collaborating with people who are very, very similar to themselves in terms of the research they've done most of the time. And yeah, so this is the kind of the decision tree, so to speak, is that given that they've successfully collaborated with someone, they can either go down the same task type or different task type route. And then given that they've gone down the same type or different task type route, they can go down either similar or different research level route as well. And I'll just check it's in there. Yeah, so when they do, oh sorry, actually I think I've forgotten link persistence, I apologize. The links persist on average for 3 years. So this was done by kind of modeling probabilities over a uniform distribution of the link degrading or not. And that happens on average once every 3 time steps. Uniform distribution. It's just as a way to simulate it happening a third of the time in the network. We weren't able to find any figures for whether those with more links were more likely to kind of drop collaborators, or those with less links were more likely to drop collaborators, or whatever. So we just did it equally for every single edge in the network.
So uniform is 0 to 6.
Yeah, but in the code it's 0 to 3, and then if the link each link chooses a number defined uniformly over 0 to 3, if it's 1, they do it. And yeah, sorry, when people collaborate, two kind of different things can happen. So if they're of a different task type and they collaborate with someone else, then it gives them the chance for a joint venture. That increases their probability of either having a successful radical research project or a successful incremental research project in the next time period by 0.025. And that's, we found that's because from a panel data study conducted by Santa Maria et al. Of general high technology industries. They took a large data set of Spanish high technology firms and were able to econometrically tease this out. Whereas if they're of the same task type, then ideas can diffuse between them on the network. And the diffusion model is the standard kind of social learning model from Penn and Young with heterogeneous priors. So labs have prior probabilities that they think that the other person's innovation is going to be good or bad. These are distributed normally across the labs in the network. And if they observe the innovation being kind of good enough to overcome their kind of prior about it, overcome whether they think it's bad or good before, they will adopt it, and if not, they will not. And this happens every single time period at the end of each time period for all of the labs of the same task type which are connected together.
So what you've written there, you said probability of success equal to 0.025?
It increases by 0.025.
From its previous terms, probability of success.
Yes. So yeah, firms can also enter or exit the kind of AI space. And we were again able to find from the venture scanner data set specifically a statistically significant log-log relationship between funding in one time period and the number of firms in the next time period. So basically the kind of story for this that you might think of intuitively is that as funding, as kind of venture capitalists and so on invest in the market, more people create startups, which then hopefully if they collaborate more and innovate well can lead to positive feedback loops where there's more funding, creates more startups, so on, so on, so on. And funding is driven as before by the number of innovations in the previous time period. And this creates the kind of positive and negative feedback loops in the model, which I will talk more about later. Okay, so now on to some more results-based things. So in order to kind of test that the model was good, that was correct, and to calibrate some of the parameters, we performed a Monte Carlo simulation on data that we'd gotten for the research level of supervised learning amongst US firms in 2000. And basically what we did is we ran it forwards and saw how close it got, or how close the median value got to the value for this which we use in our model, which is 0.61, as on the earlier slide. And we were able to the model was reasonably successful at forecasting the level of automation in 2017 from the level of automation in this in 2000. So we got a median value from the predictions of 0.574, and the actual thing is 0.61. The reason we use the median rather than a mean or so on is because, as you can see from the distribution I've put up here of the observations that we got, distribution of predictions the models created, it appears to be heavy-tailed, or at least have a large enough tail that it can't infer a normal distribution from it. And the kind of reason for why this might be are the feedback loops I kind of mentioned earlier. So in the model, as firms innovate more and more successfully, it causes more and more funding to flow into the space, more and more startups start up because of the level of funding being increased in the overall space. And hence, there's a greater success overall. There's a greater probability over the entire network of there being some kind of large degree of innovation, which again boosts funding and so on and so on and so on. And again, we can generate negative feedback loops as well with the same thing. So if the firms aren't particularly successful in a time period at innovating, if none of them do very good research and so on, it tends to dampen the level of research overall throughout the thing. So there's less funding in the network, there's fewer firms birthed, or even a drop in the number of firms in the network. Certain firms will die out. And hence, again, this tends to feed back into itself and repeat the process over and over again. Because if you have fewer firms, you have a less chance of success, or sorry, less chance of there being large innovations network. So again, a lesser chance of there being large influxes of funding. And so the kind of cycle repeats itself. And yeah, so this was an individual plot that we got from this, just to demonstrate some of the shapes of the kind of curves the model is generating. Yeah, this was a individual run out of the Monte Carlo simulation I talked about, from which it got to, I think this is 0.584 or something like that, forecasting forwards from the level we worked out, level of automation in 2000 to then the level of automation in 2017. And what you can see here is that the model produces quite nicely. I think, before I say this is also just a uncalibrated run, unfortunately. We didn't get time before this seminar to do a fully calibrated run of the entire model, but this is an uncalibrated run, by which I mean, I should explain further what I mean by that. A couple of the parameters are slightly different in this to what they would be in the main model. So specifically the social learning parameters that I mentioned earlier, from the Penyon-Young model of social learning. It's specifically the agent's priors. The distribution for that in this is different to what it appears to be in the empirical data, because we produced this plot before we had a chance to calibrate that. But as you can see from both of those kind of plots.
The individual colors are,
oh, yeah, sorry. The individual colors are the same as the colors that I met on the network diagram from earlier. Sorry, I should have come back to this. So yeah, each of these colors represents a different task area and the firms working in them in the aggregate. And these are again grouped color-wise by the McKinsey type groups that you see back here. So
Can you tell us which one is the one that has a really huge phase transition there?
okay.
Which one was that one?
That is navigation. Yeah, well, I wouldn't read too much into this. This particular run of the model. As I said, this is only one run over it. And because of the feedback effects within individual task areas, if there is a big innovation at the beginning, it generally leads to something like this. This particular curve would be, yeah, and also the fact this jump though would be one of the firms has pursued a radical innovation and happens to have very, very unlikely drawn a large value from the log normal distribution. Specifically drawn, it looks like about 1 from the distribution, which, as I said, is centered around 0.0001 in terms of its level.
so are they randomly assigned, or is the parameters or navigation in your model the same as lifted from some sort of real world assessment of navigation's parameters?
In this case, yes, apart from the social learning parameters. As I said, but the social learning parameters are quite important, and I'll talk about this in a second. So yeah, I wouldn't read very much into this. This is more for illustration than anything else. But what you can see from these kind of models, the useful thing you can draw from these kind of looks is the kind of broad shape and effects that you can see. So as you notice, as you can see both in this and here, you're getting these S-shaped curves that are being generated in the model. So yeah, see the S like this, for example, or sets of linked S-shaped curves. So this would, for example, be 1, then 1, then 1 up there. You see what I mean there? And this fits quite nicely. This fits quite nicely with empirical observations generally in the technology literature. It's this thing called linked S-curve theory, you might have heard of, which is that technology, both in its adoption and in kind of its generation, follows kind of S-shaped patterns, like the ones you see there, where there are jumps, and then people kind of like, the story at least is, people then start utilizing this new technology from the jump, more and more and more, apply it to more and more problems, solve those problems, but then eventually it kind of dries up. You can only use it for so much. It kind of is quite flat, the innovation curve, until suddenly someone else makes a radical innovation, invents the new like plane, or invents a new type of machine learning algorithm or whatever, and then the process starts all over again. It's kind of similar to Kuhn's notion of a paradigm shift in science. I've heard that. So we generate those curves, which is quite nice because, I mean, that's what these kind of models hope to generate. The McKinsey model specifically also tries to generate these curves as well, and only does so over a much flatter and longer time horizon. I haven't got a graphic for this, unfortunately, but it kind of reproduces a clustering effect we also see in the empirical literature. So firms tend to group in terms of the technologies that they have and use. So, for example, in HR automation, all of the firms use roughly similar supervised learning algorithms, for example. In photovoltaics, use similar types of solar panels, so on. And that was observed by Cantor and Meader, and we are able to generate this in the model. As I said, unfortunately, I don't have a graphic for it. The firm's research levels tend to be very, very closely clustered until one makes this radical jump, one makes a successful radical innovation, and then the firms kind of follow and catch up to it, and then it stays around there. You might think of it as as these kind of bits in the S-curve, the flatter bits. I'll use the navigation one because it's so big, it's easier to show it. These kind of flatter bits are where the firms are more clustered together, and as you get the jumps, they become less clustered and more clustered again there. Yeah, and the tail in the distribution of results is also quite encouraging in terms of the analysis. So it fits with the kind of sensitivity to initial conditions and feedback loops you see in real life technology spaces. So if you think of an example, if the Wrights hadn't stumbled upon a way of combining bicycle engineering with new canvas materials and so on to make their planes, it might have delayed the kind of automated the flight, human flight by about 10, 20, 30 years, whatever. Them doing it, them chancing upon this kind of combination of things to make this innovation, then vastly changed the time series of innovation in flight. And that's kind of similar thing that we can see in this, as the perfect example being this navigation line here. The fact that at this point in the model, a firm has chanced upon a really radical innovation has led to a massive change in the overall plot, specifically lifting it up over here. And you can also see it again quite nicely in these bottom plots as well, actually. I'll just talk about this quickly, which are the kind of social and emotional learning type states. Again, I don't want to read too much into this kind of a plot, but the fact that there hasn't been any large innovations in this space over this time period seems to have meant it's quite constrained. It stays quite low. The level of innovation, so level of automation in the overall task type area stays quite low compared to the others. Whereas the ones like this, where you've got the jump, it kicks off a cycle in the model, which then causes more and more innovation, and so on.
Is the success rate
Um,
of an innovation or collaboration?
The success rate is, yes, it is constant. I'm trying to think of the figure now. I think, is it somewhere like that? Yeah, sorry, I think I forgot to put it in the slides. I apologize. But yes, so it's a constant as an exogenous thing. The firms have a fixed probability of success for each of these things, which, yeah, I think he did come in earlier because we talked about how that can be increased by joint ventures. Joint ventures increase it, whereas in terms of the information diffusion part of the model, what that is that's firms explicitly adopting other firms' innovations and ways of doing things.
So can we know about your success by some sort of Bernoulli trial on a terminus basis, is that right? Or is there, how is the success distributed?
The success is distributed. Do you mean by that for each individual agent or across the network as a whole? Each individual.
Could be an exponential with a rate. You talked about a rate, and you talked about probability of success.
Oh yeah.
So a rate would imply some sort of exponential distribution plus on process maybe. But a probability of success is what you give to the
Yeah, this is just me using words not very well, I'm afraid. It's a fixed, so in each time period, each agent has a certain fixed probability that for each innovation they try to carry out, that it will be successful or not. And then the actual size of the success, in a way, the kind of increase in the increase in the level of automation that will be caused by their innovation, so kind of how big the innovation is in a certain sense, is then the thing that's defined across the distributions, as I mentioned before.
Defined it across the distribution. So how would
Yeah.
that be distributed?
Well, as I mentioned earlier, the incremental innovation size is distributed across a uniform distribution between 0 and 0.001. And radical innovation, the size of radical innovations is distributed log normally to capture the fact there are these occasional, very, very large innovations, but most of the radical innovations we observe are still quite small themselves. And the mean for that is centered on the upper edge of the.
Log normal, it's very important for you to say what the mean and the standard deviation. Because that's what really drives the skew of log. And so what was the SD?
Yeah. The standard deviation is 0.0002. So, or the standard deviation of the non-logged value,
So the mean was what?
0.0001.
So it's 1 over, what sounded like 1 over 1,000 or 1 over 10,000?
This is better mental maths than I can do. Sorry, I'd need it. Yeah.
What was the mean with relation to the standard deviation?
Twice. Sorry, the mean was half the standard deviation.
Oh, good. You got a very skewed curve.
Anyway, areas in terms of, like, as you probably mentioned from the questions as well as from the presentation, there's a lot of further research that can be done on this model. Yeah.
There's a lot of knobs to turn. I mean, all these questions are things you could change.
Yes, they could be.
Not at the end. So.
Yeah, definitely. For now it is, as you mentioned earlier, kind of intended as a fixed point forecast model. So we're trying to fix all of the inputs empirically and then see where it goes rather than trying to allow sensitivity analysis and so on. But this is something you can build on further. Specifically, what we were thinking of what would be good areas for further research, what we thought would be good areas for further research, would be to get better data sets in a certain way. The data sets we had seemed good, but could always do better with a full survey of AI firms and labs. Some of the pieces of data we had to use were older than we might like. Specifically, the network characteristics were older than we might like. You could try and endogenize some of the remaining parameters. So myopia is what it's called in the model, the probability of incremental versus radical innovation. Intuitively, it would seem that if you're more successful at doing these kind of big radical moonshot type projects, you're more likely to do them in the future. But we couldn't find any paper which had any empirical data on that, whether it's more.
Did you also have any data on likelihood of collaboration with firms perhaps that had collaborated before to account for that, or collaboration between firms, maybe two firms are collaborating and the likelihood then that one that's collaborating with another would collaborate with that third?
So we had the clustering coefficient for the network, but we didn't have any data on the individual nodes probability of repeat link forming, basically. Unfortunately, that would be a thing that a full survey would allow us to accomplish. And then specifically also, this is only American firms that we've been using at the minute, firms based physically in America. In order to get actual forecasts for level of automation by 2050, you need to include all the world's firms, obviously. It's not just American ones working on this problem. So expansion to that would be very, very useful as a further research direction. Unfortunately, my time here was time constrained, so we didn't have a chance to do that. But we're hoping to maybe try and do that in the future. And then generally, this model isn't intended as an AI-specific model. As the processes I've talked about aren't specific to firms working on AI. It's not like only firms working on AI innovate, though Silicon Valley might want to tell you otherwise. Other firms do as well, those in photovoltaics and in biotechnology, other things like that. So expansion to other high technology industries would be possible. would be possible, and would hopefully be useful in forecasting those industries. You need to recalibrate a few of the parameters that I've mentioned because they are intended to be empirically correct for AI firms, but the actual framework of the model is there. And hopefully at some point soon, a framework for the model will be going up on somewhere like GitHub. There's a Python version and a NetLogo version. I warn you, the NetLogo version takes a long time to run. Even with the kind of common tricks for doing scientific modeling in NetLogos for reducing the runtime, it is still very computationally heavy in the NetLogo language because of the ways lists and stuff like that work in NetLogo. But the Python model is built in the Mesa module, which was very good and very useful for doing it. And yeah, should hopefully go up on GitHub at some time soon if anyone does want to apply it to anything else. And any more questions?
This is very much work in progress, so Kieran's a bit heavier suggestions for how we're going to bring it to further fruition.
What year are you in university again?
I'm going into my third and final year of undergraduate degree.
Kieran, when you get a question, please repeat it for them.
Okay, sure.
Would you go back to your next previous slide? The one with the
Okay.
future? So, when you started this, you might have had in mind a policy question someone would be asking, or giving an answer to a question somebody might have. And I'm trying to figure out, to give you some guidance as to which of these 4 bullets you might pick from or the like. I'm trying to elicit what question do you think you need to answer here, and which of these moves you in a direction to helping answer a question that somebody needs to ask with regards to public policy.
Okay, so yeah, the question was for the people on live stream. What question did you have in mind when you were making the model, and what kind of parameters would be useful to be able to be varied in order that you could answer policy questions? If I got it right. What's the most important to do? The specific question that I was thinking of when I was making this model was the more labour market outcomes. So by 2050, what will the labour market be like? And kind of a way to do that with this model would be to expand it into a labour market prediction model. Put some kind of market matching mechanism on top, or kind of mechanism which matches these types of these task types to specific tasks, specific jobs. And yeah, that's something we're definitely interested in looking and doing in the future. In terms of actual sensitivity analysis, in terms of more specific policies than that, I think definitely having kind of exogenous funding increases and so on would be quite useful question to answer, because I mean it's quite useful to know whether these investments in large technology firms and so on are actually driving any form of innovation forwards. And if so, how much, say, public investment in artificial intelligence startups and so on, in university research labs, how much benefit that would bring. And I think, yeah, that would definitely be something useful to be able to put in. Also, something which is quite useful, and we noticed while parameterizing the model, was that when you go back to this kind of curve here, when you change the individual's prior beliefs over how good other people's innovations are, the benefit from those innovations, you get roughly the same shapes of curves, but they're moved up and down at very, very different outcomes. So in cases where individuals have very strong beliefs that other people's innovations are good innovations to use and adopt, so you might think of it as kind of a high rate of informational diffusion within the system, you get very, very high forecasts. So a good policy question that might be able to be addressed is kind of the diffusion of information, both in academia, for labs working on this, and amongst firms. How much increasing kind of the rate of diffusion of that would increase the kind of levels of automation we can see in the future, and I mean, that would be useful because that seems to be a reasonably easy problem to fix. Policy-wise, wouldn't take the government spending millions and millions and millions on AI startups, for example, and could potentially lead to large increases in the levels of automation in the future, and hence potentially future prosperity and so on. I don't want to understate the job market question, though, the initial thing I said, because obviously trying to predict the labour market in the future is very, very important because people's livelihoods depend upon it, right? And being able to know better, even just from fixed point forecasts rather than varying anything, the kind of state that the labour market will be in 2050 might be able to help governments and so on formulate better public policy. Though that sounds quite grand for my 10-week project, to be honest. Yeah. Well, so the question was why an agent-based approach rather than statistical approach, or like a systems mathematical modelling approach, and whether there are any emergent behaviours that came out from that. Well, to be quite honest, the agent-based approach was in part because that's what I can do. In a sense, I don't have a large background in equation-based system modelling. But it's also because it seemed a more obvious approach to take when reducing the kind of uncertainties you see over predictions than simply a systems-based approach. Because it would seem, again, this is just personal intuition rather than anything else, take it with a truckload of salt, that you would need to kind of build in more uncertainty, more guesses by doing it as an overall statistical or equation-based approach. By simulating the individual agents directly, you're able to be more empirical because getting firm-level microdata, and by simulating their behaviours individually, you're able to hopefully remove the uncertainties that you might see if you just programmed overall behaviour. So you might not know roughly the proportion of firms in a certain time period that will do X, but by simulating them and seeing that they do X, you can find that out. Emergent behaviours-wise, the feedback loops were definitely a very interesting emergent phenomenon in it, which you wouldn't necessarily capture in an overall equation-based approach. As you could see, the regression analyses equations were there, but it was the heterogeneity amongst individual agents when pursuing innovations that kind of really drove the feedbacks. Since it only took like one agent to have a great idea to drive these kind of feedback loops, and hopefully in the future, when we have more time and we've been able to run the model out with more firms and so on, we'll be able to quantify this and show this in a better way than just me saying it. Bill? Well, I mean, you might say that. I don't really want to comment until we've got good approaches. The 0.4 to 0.6, I'm going to emphasize this is, okay, sorry, again, the label on this is wrong. That might be misleading. This was the target data this was the level that we observed in 2000, and this is the level that we observed from checking the ONET data and so on in 2017. So the 0.4 to 0.6 is the target data. Sorry, I used the same piece of code to make all of these plots in ggplot, and I obviously forgot to change part of the title. I apologise. Yeah, it's only over 18 years, yeah. As I said, because we didn't have time to, unfortunately, run a fully calibrated version of the model multiple times to get a good prediction. I'm not able to show you a prediction now, but hopefully, I guess, given that we only had American AI firms in the model, it would be misleading. Or it interpreted as a 50% increase in what can be done by automation. So as I said, it corresponds to the kind of level that the task is at. So say 0.45 is roughly kind of average human level, whereas 0.61 as ONET classify it is like kind of slightly better than average human level. So quite a good human would be able to do in terms of recognizing patterns in this case. That's true. I'll try not to. Okay, so sorry, I should have made this clearer in the presentation. The data, it's actual data, and we were only able to, unfortunately, find it an accurate level from 2000 to 2017 for FMs, and each data point there is a yearly point, unfortunately. Ideally, we'd like to have it more fine-grained, and again, that's where a survey of the whole industry could come in useful. But yeah, so most of it is empirical data collected by the different organisations that I mentioned before, and some of it is specifically the network stuff that is generated from overall network data on the overall network level properties that we had as well. But we had to generate some of that stuff synthetically. Well, we have here, because it's 2000 to 2017, this would be 17 individual points on the graph. Yeah, and it's to predict through to 2050. Well, we didn't directly look at it. We did test for autocorrelation amongst different things, and nothing significant came up. Yeah, as I said, hopefully when it will be properly built and stuff, it will be going up on the GitHub page, KU, at some point soon. Potentially with permission from people running Mesa, maybe as part of the Mesa library of Mesa models and so on. That would definitely be useful to have. I assume that would come more on when the kind of building in the labour market data type thing, because obviously if jobs are if some very high demand jobs are automatable, that would probably introduce feedback, or intuition is at least it would introduce feedback where it caused greater demand and so on. We didn't attempt to explicitly represent that in the model. It's kind of represented by proxy within the innovations funding regression model. But yeah, they only talk a little bit, I think. They talk a lot about potential consumer feedback rather than trying to do actual stuff, if I remember it correctly.
So the minimum number of rules such that so what rules do you think you take out? You've got 5 or 6 rules. Take out
for the linked SCurve to disappear, the radical incremental innovation. innovations. If they couldn't pursue two innovation types, it would likely be a linear curve rather than S-shaped. Although in part it's fueled by, I would say, take out two rules. In a sense, if you took out the social learning rule as well, because you could still, in theory, generate a kind of S-type shape with just incremental innovations, purely because some firms will innovate slightly, the other firms will adopt it. It would be something more like a little kind of wavy thing like that. It wouldn't be as large or as pronounced as the kind of S-curve you see in real life, and the S-curve you see in this. But if you took out the diffusion model as well, the diffusion part as well, you would probably generate, I would think, a kind of a linear process. Yes.
One more question.
Yeah, so sorry, I've realised I've forgotten to repeat the questions for the microphone, so I'll do it again. It was what advice would you give to someone trying to make agent-based models like this? I would say starting from the empirical data rather than starting from your own intuitions, hypotheses, and so on was very, very useful. Because there are a few kind of toy agent-based models of this kind of process. But ultimately their use is very, very limited because it's just what the kind of prior that the person plucks out their head for whatever it might be that they're kind of using to put in the model, and obviously there's no kind of, it won't necessarily match up to real life. So I'd say starting from micro-level empirical data and building upwards would be what I'd recommend. Mm-hmm. Mm-hmm. Yeah, that is true. The point was that toy models can be useful for kind of understanding the actual processes that run under. And yeah, I think that's true to an extent, but if you were more what I meant was if you were trying to use a toy model to say forecast things, it wouldn't be very useful. And in cases where behavior isn't necessarily totally apparent, for example, your intuitions about certain behaviors might be entirely off the mark. So I think for that reason, it's kind of useful. It might be useful to make models of the individual processes and stuff like that beforehand, but when you're actually building your main model, it's useful to start from the data, purely because, yeah, what you think is going to occur might not be what actually occurs. Like, I mean, what I thought would occur for some of these parameters was very, very different to what it in fact was. So.
Series of limited growth curves. Growth capacity, the capacity gets increased, only by another factor, whatever, and it goes up. So starting with exponential growth, you get to the inflection point, which is exponential approach to that, and sequential. That's what it is. That's what it's called. In order to do that, you have to put more than you have to put a lot more than 5 minutes for every capacity. Basically, you want to overfit this thing, take it down there.
before
That's
we
nice to
go,
know.
let me just mention that you'll be around for several more days, or a few more days.
Hmm.
And so, and it'll be great to connect off on. Thank you.